Alright, here we're going to be talking about the altitudes of right triangles. So an altitude is a line segment within a triangle that's drawn from a vertex to the opposite side, and it's perpendicular to that opposite side. It's a line segment that passes through a vertex, and it's perpendicular to that opposite side. So from each vertex, you can draw a line, and making sure that it's perpendicular to the opposite side, that is an altitude. So actually every triangle is going to have three altitudes. So I drew that first one from this point straight down to the opposite side, creating that right angle. Now from this vertex to its opposite side, creating another right angle. And then from this vertex to its opposite side, creating another right angle. So every triangle has three altitudes because it has three vertices. We're actually just going to be concerned with altitudes of right triangles here, because a special kind of situation is going to pop up. We're going to create three similar triangles. If an altitude is drawn through the hypotenuse of a right triangle, then two similar triangles are actually created, and they're similar to the original triangle. So we have this right triangle here, the original triangle, ABC is a right triangle, and then we create this altitude, CD, which actually creates now 1, 2, 3 similar triangles. The two small triangles that were created inside of that triangle are similar to each other, and they're similar to the original triangle. So I'm thinking about my original triangle. I have my right angle at C. So I have C, the long side is CB. So I have CBA as my big triangle. I'm just trying to reorient these so I can see that they actually are similar. Now I'm thinking about my middle size triangle. That's this triangle here. The right angle is at D, the long side is DB, and then the short side is DC. And then I'm thinking about my small one here. My right angle is actually still at D. My long side is DC, and then my shorter side is DA. So I have a right angle in each of them. And I know that these angles are all going to be the same. One of those pairs should be obvious. Obviously, angle B is congruent to angle B by the reflexive property, but it's also congruent to this angle C. This angle C is what we're talking about in this triangle. And there's a really easy logic to this. If angle A, angle B, and this 90-degree angle add up to 180, well, in this triangle, I still have angle A, I still have that right angle, so the leftover part has to be the same as this angle B that I have here. Well, here we just happen to call it angle C. But this angle here has to be the same because it's complementary to angle A. They both add up to 90 with this angle A that exists in both triangles. It exists in the small triangle, and it exists in the big original triangle. So actually the same kind of thing is going to happen with angle C on the other side. This angle C, that angle and that angle are complementary, and I know that this angle and this angle are complementary, so they have to be congruent. They're congruent complements. So by orienting them a little bit differently, I can see that they have to be similar. Now I'm just going to write out those similarity statements. Triangle CBA is similar to DBC, which is similar to DCA. And we haven't talked about this, but we do have the transitive property of similar triangles. If these two are similar and these two are similar, we can jump over the middle one, assuming that all three are really similar to each other. So we're going to use this to find some missing sides. We're going to try to find side DB. I'm going to label that with X. If AD is 4 and CD is 6. So the first thing I want you to do is actually just redraw these triangles so they're oriented the same way and we can see which sides are corresponding. So I'm going to just redraw triangle ACD. Actually exactly as it is. I have my right angle down there, 4, 6, and I have triangle ACD. And now I'm going to try to redraw triangle BCD so that it's oriented the same way, so that my angles are all lined up with their corresponding angles. This is kind of the easiest version of this type of problem. I'm going to imagine this triangle just tip over So that point C lands down here. Point D doesn't really move. It just pivots by that point. So point D and C are going to lie flat on the ground. This point comes down. And point B is going to come up to the top. So point B is going to end up here. The reason I know that's the orientation is because angle B there is congruent to angle C in there. So I just want those two to line up. And then I could rewrite what I know about that. Well, I know BD is X, that's just how I labeled it. And I know that CD down here is 6, which is actually all we're going to need. We have a pair of sides here, and we have one of the two pair of sides there, so we can set up our proportion. 6 over 4 is the same thing as X over 6. So we're lining up our corresponding parts. I know that 6 and X are corresponding parts in those two separate triangles, so they should be lined up across from each other. You could also think about this as a scale factor. If you think about what times 4 would get us up to 6, you could apply that same scale factor to to 6 to get to X. I just like lining these up as a proportion, just because a little bit of it, because it's satisfying. It just lines up correctly. I know that these two are corresponding parts, and so are these two. And I think I did all that work just to get these to look the same. I want to make sure that I finish this off in a systematic way. So I'm going to cross multiply, get 36 equals 4x, and then divide by 4, so x equals 9. So the length of DB has to be 9. I definitely want you, at least in the beginning, to draw these triangles just oriented the same way so that you can match up those corresponding parts. Right, number 2 is saying that AD is 2, DB is 8. We're trying to find CD. So I'm going to label that as my x this time. This is using the same two triangles. I'm still really comparing this small triangle to the medium-sized triangle. I haven't really done anything with my big triangle yet. But I'm going to reorient these the same way. Actually, I'm going to leave the first triangle the same. I have 2x, and then the same kind of reorientation. I'm going to imagine this tipping over. The bottom side is x. This upright side is 8. And I have that same relationship. I have my two legs paired up. So I can write x over 2 is the same thing as 8 over x. And then I'll cross multiply. I'll get x squared equals 16. So x is either -4 or +4. But since we're talking about a length, it can't be a negative amount. It can't have a negative length. So x is +4, or the length of CD is 4. All right, on number 3, they're giving us AD and DB, but now we want to find AC. So you really want to think about what two triangles can be useful. I'm going to redraw all 3 triangles just so I can see what could be useful here. I'm going to draw ACD. I have 3, and I have x as the hypotenuse. I'm going to redraw that middle-sized triangle, orienting it the same way. I have nothing for the bottom side. I don't know the hypotenuse of that one either. This is the hypotenuse of that one. This is the bottom side. I don't know those two, but I do know the upright side is 6. So that's not terribly helpful. None of those sides really match up. I don't have any pair on either of those. So I'm going to redraw the big triangle. I'm going to take triangle ABC and redraw that also. A lot of the times I think about this as the small side, the big side, and the hypotenuse. I know the hypotenuse is going to be 9. That's 3 plus 6. So that's going to be 9. And I can see my shorter side here, or at least what appears to be the shorter side, is x. That actually drops to the bottom here. That's not the most reliable way. You do want to imagine how you would turn this so that the angles will line up. But I know that this angle, and this angle are all going to be the same. I know it's true in the first two because I just did examples just like that. But then in the big triangle, I'm looking at angle B coming up to the top here, and angle A, which is exactly what I drew here in this first triangle. That's also angle A. That has to line up. with that bottom left corner there. Alright, so I know that my bottom side here is x. I know that this is 9. And actually that's really what I need. I need to find two pairs that can match up in another triangle. So I have 9 here, I have x in this one, and I have 3 here, and I have another x. As long as we're in terms of the same variable, we should be able to solve it using just those two triangles. This middle-sized triangle is not super helpful on this one. So I'm going to set my proportion just using the big triangle and the small one. 9 over x is equal to x over 3. So I'm going to cross multiply and get that x squared is 27. So x is the square root of 27. If you'd like to leave that as decimal, you can. If you're going to leave it as a radical, I want you to simplify it. There's a 9 in here and a 3. 9 is a perfect square, so you can do the square root of 9, which gives you 3. That doesn't simplify, that's just going to stay as the square root of 3. Again, I'm sure most of you prefer decimals. Use decimals if you want. All right, number 4. We're given BC, which is 6, and AD, which is 5, and we're trying to find the length of DB. I'm going to do that same thing that I did on the last one. I'm going to redraw all 3 of these triangles just so I can see them clearly and make sure I know which parts I have to actually use. My smallest triangle, I just have the bottom side, I don't have the hypotenuse or the upright side there. My medium triangle, I have the hypotenuse of 6, I have the upright side of x, I don't have the bottom side. And then in my big triangle, I have the upright side of 6, I don't have the bottom side, but I know that this is x plus 5. I know the hypotenuse is these two lengths put together, which is x plus 5. That's going to be helpful here because this side and this side are my two corresponding parts with this side and this side. And they're both in terms of x, so I should be able to solve for that x. So I'm going to line this up as x plus 5 over 6, which equals the same corresponding parts, 6 over x. I did hypotenuse over the upright side, so I'm going to do that same thing in the other fraction, the hypotenuse on top over the upright side. Now I'm going to cross multiply. X times x plus 5 equals 6 times 6. I'm multiplying both those together. 6 times 6 is just 36. The other one's a little bit more complicated. I have to distribute that x. I'm distributing x into both of these. X times x is x squared. X times 5 is just 5x, and that equals 36. To solve this, I'm actually going to end up factoring. There's multiple ways you can do this. You can do this in Desmos where you just graph it and find the solutions, but I don't mind factoring this, especially because I know it's going to be whole numbers. So I'm going to subtract the 36 from both sides. I'm running out of room, so I'm going to erase some stuff. I'm going to subtract 36 from both sides and get that x squared plus 5x minus 36 equals 0. And then I'm going to factor. I know that 4 times 9 gives me 36. I know I need to add up to a positive 5, so I'm going to change that to a positive 9. So my two solutions there are negative 9 and a positive 4. I can't have a length that's a negative number, so I'm just using my positive solution of just positive 4. Alright, I hope this helps. Use the rest as practice.